Unraveling the Mystery, the Hunt for Quantum Gravity's Fundamental Theory. Singularities, the mysterious cosmic enigmas that challenge our deepest understanding of the universe's fabric. Both the birth of the cosmos and the core of black holes present puzzles so profound, they threaten to upend our best theories of gravity. But here's where it gets controversial. Despite decades of research, these singularities stubbornly resist explanation or elimination, suggesting there's far more to discover at the edge of space and time. These enigmatic points, known as singularities, appear as breakdowns in the smooth weave of spacetime predicted by Einstein's general relativity. Simply put, Einstein's theory shows how matter and energy bend space and time, creating gravity. Yet, when an immense amount of matter is compressed into an incredibly tiny region, the equations predict that spacetime curves infinitely sharply, yielding gravitational forces so strong they become unimaginable. This hints towards singularities at the heart of black holes and at the instant of the Big Bang when the universe ignited. Yet, most physicists are skeptical about the literal existence of such extreme conditions. As Hong Liu, a physicist at MIT, explains, these singularities are often viewed as mathematical artifacts, signals that our current theories cease to work properly rather than actual physical objects occupying the cosmos. They highlight the limitations of general relativity, suggesting it's only an approximate description that breaks down under extreme conditions. The true nature of gravity likely demands a more fundamental framework, quantum gravity, that seamlessly merges quantum mechanics with Einstein's geometry. The challenge is, this deeper theory has proven elusive. Even as researchers work tirelessly to unify these frameworks, a series of landmark mathematical proofs, starting with Roger Penrose's 1960s Nobel-winning insights, firmly demonstrate that singularities are inevitable consequences of the space-time fabric, even in scenarios incorporating quantum effects. Initially, Penrose proved that in a universe filled with nothing but classical space-time, singularities must form under reasonable conditions. Later research extended this to universes populated with quantum particles, showing singularities still persist, even when quantum particles slightly influence the curvature of spacetime, a scenario closer to our real universe. This trilogy of proofs forces a profound reckoning. Singularities might be real, physical features of the cosmos rather than mere artifacts. They signify points where the fabric of spacetime frays beyond recognition, halting clocks and rendering travel or interactions impossible. Understanding these boundaries isn't just about fixing equations. It demands rethinking the very essence of space, time, and the laws governing the universe. The story begins with Carl Schwarzschild, who in 1916 discovered an extraordinary solution to Einstein's equations revealing a singularity, a space-time vortex where the curvature grows infinitely steep. Decades later, what we now call black holes were understood as physical objects that could trap even light behind an inescapable event horizon. In 1939, J. Robert Oppenheimer and Hartland Snyder calculated that the gravitational collapse of a perfectly symmetrical star would crush its mass into a singularity. But in reality, stars aren't perfect spheres. They wobble and churn, raising doubts about singularity formation. Then came Penrose, who, in a groundbreaking 1965 paper, showed it doesn't matter if the trapped region's shape is irregular. As long as light cannot escape that trapped surface, and gravity remains attractive, which it does when energy is positive, a singularity must form. His proof elegantly generalized and deepened our understanding of spacetime's fatal flaws. Stephen Hawking extended this logic to the early universe, demonstrating that the Big Bang itself was a singularity, a beginning point from which all space and time expanded. But singularities, by their nature, present a paradox. They disrupt predictability and break the laws of physics as we know them. If trying to track a particle into a singularity yields infinitely uncertain outcomes, how can physics remain reliable? This problem fuels the quest for quantum gravity, a theory that'll offer coherent predictions even when spacetime itself becomes fuzzy and uncertain. Quantum mechanics reveals that matter isn't fixed in one state but exists in superpositions, multiple possibilities simultaneously. Since spacetime bends in response to matter, it too should be able to exist in such superpositions, leading to the expectation that gravity operates quantum mechanically. Yet, capturing exactly how this works remains the holy grail of physics. Scientists picture their search for quantum gravity like peeling an onion. At the outermost layer, classical general relativity reigns supreme, ignoring quantum effects. Penrose's theorem belongs here, proving singularities in a purely classical universe. In the middle layers, quantum effects start to seep in. Here, particles are quantum, but spacetime remains classical or semi-classical. Aaron Wall pioneered exploration of this realm, incorporating insights from Jacob Bekenstein about black hole entropy, the mysterious measure of disorder related to their surface area and quantum particles nearby. Wall redefined Penrose's trap surface to a quantum trap surface, considering both geometry and entropy. His 2010 breakthrough showed singularities still form even when quantum particles influence the system, suggesting deeper quantum effects alone don't immediately resolve singularities. But the onion's core represents full quantum gravity, where both spacetime and matter are inherently quantum and entwined. In this realm, classical notions like surface area or smooth geometry may dissolve, making existing singularity theorems inapplicable. Still, some physicists believe even this ultimate theory will preserve the notion of singularities as boundaries, places where familiar physics truly ends. Recently, Raphael Busso advanced the discussion by delving into quantum realms where spacetime does react to quantum particles, including shrinking black holes due to radiation. His theorem, published in early 2025, demonstrates that singularities persist even under these more realistic, but mathematically complex, conditions. However, he assumed an infinite variety of quantum fields, unlike our universe's limited set of particles, prompting debate over the real-world applicability of this model. Controversy arises when considering alternate ideas. Could singularities actually be gateways to other universes? Or might the Big Bang be replaced by a Big Bounce, where a previous cosmos contracts then rebounds? These bounce theories, often relying on semi-classical physics with negative energy phenomena, face tough challenges from the newer theorems, which suggest that accommodating these ideas might violate fundamental laws like the generalized second law of thermodynamics. Surjit Rajendran, who researches bounce models, remains optimistic, arguing that even the generalized second law isn't absolute. Rejecting it could open ways to avoid singularities, hinting that spacetime might continue in unexpected forms beyond current theoretical boundaries. Ultimately, the hunt for quantum gravity and the true nature of singularities forces physicists to confront uncomfortable questions. Are these points where space and time literally end, or do they signal new physics beyond our current language? If singularities survive the ultimate quantum theory, our understanding of position, duration, and curvature may need to be replaced with entirely new concepts. As Jeff Pennington suggests, the quantum state describing a singularity might transcend familiar ideas of time itself. So what do? Quantum revolution, unraveling the secrets of gravity and space-time. The foundations of quantum reality are shaking. New research reveals how gravity and space-time significantly influence the quantum realm. In a nutshell, microscope researchers are investigating the intricate relationship between quantum mechanics and gravity through the use of sophisticated quantum networks. Milky Way. These quantum networks have the potential to create a worldwide quantum internet, employing qubits and entanglement to ensure secure communications. Magnifying glass delta left. The goal of this research is to explore whether gravity can modify quantum mechanics, which could lead to a comprehensive theory of quantum gravity. Rockets. Such advancements could transform our understanding of the universe and reshape the very foundations of physics. In a remarkable advancement in the field of physics, scientists are diving deep into the intricate connections between quantum mechanics and gravity. Their groundbreaking work could unlock a more profound comprehension of the fundamental laws governing our universe. By leveraging advanced quantum networks, these researchers are striving to reveal how the interaction between the curvature of spacetime and quantum theory might bring us closer to a unified theory of quantum gravity. As they challenge the limits of contemporary science, the potential ramifications for technology and our understanding of the cosmos are immense. This initiative could fundamentally alter both scientific theories and practical applications in ways we have yet to fully grasp. The relationship between quantum theory and gravity. The connection between quantum theory and gravity has captivated scientists for many years. Quantum networking is emerging as a crucial instrument in this investigation, with the capacity to revolutionize global communication systems. Unlike conventional methods that depend on electrons and photons, quantum networks utilize qubits and entanglement to convey information. This innovative approach could lead to a globally interconnected quantum internet, providing unparalleled levels of security and accessibility. In a recent article published in PRX Quantum, researchers Igor Pekovsky, Jacob Covey, and Johannes Borgard emphasized the potential of quantum networks to examine the relationship between quantum theory and gravity. Their research introduces a novel protocol that utilizes entangled W states, demonstrating how quantum phenomena can be detected across network nodes. By employing advanced techniques such as quantum teleportation and entangled bell pairs, these scientists are investigating how quantum theory functions within the context of curved spacetime. Could gravity influence quantum mechanics? The evident gap between Einstein's general theory of relativity and quantum mechanics presents one of the most fascinating challenges in physics. Quantum mechanics examines the behavior of matter at atomic and subatomic levels, while classical physics pertains to larger entities. This contrast raises an intriguing question: could gravity affect quantum mechanics in ways that remain elusive to us? Current experiments are designed to ascertain whether variations in spacetime might influence atomic and subatomic behaviors. Igor Pekovsky points out that although quantum theory is generally regarded as universally applicable, gravity could potentially alter its effects. The ongoing research utilizing quantum networks suggests that these networks may not only serve future technological purposes but also become essential tools for probing fundamental physics in ways that classical computing cannot achieve. Quantum networks, a pathway to a unified theory. Quantum networks are not merely technological wonders, they are also powerful instruments for scientific inquiry. By enabling the examination of quantum effects within curved spacetime, they may help bridge the divide between quantum mechanics and general relativity. This could lead to the long-desired unified theory of quantum gravity, providing insights into the fundamental essence of the universe. The innovative application of entangled states and advanced quantum techniques by researchers highlights the significant promise of quantum networks. These networks facilitate the observation and analysis of phenomena that classical methods cannot address, establishing them as a cornerstone in the pursuit of a unified theory. As these networks develop, they hold the potential to transform both scientific understanding and practical applications, opening new avenues in physics and technology. The future of quantum exploration. The ongoing investigation into the relationship between quantum mechanics and gravity exemplifies human curiosity and creativity. By harnessing the capabilities of quantum networks, scientists are forging new paths for exploration and discovery. As they continue to delve into the complexities of spacetime and quantum theory, the opportunities for technological progress and scientific enlightenment are boundless. As we stand on the threshold of a new chapter in physics, the potential for quantum networks to reshape our understanding of the universe is both thrilling and profound. Will these endeavors ultimately culminate in a unified theory that reconciles the principles of quantum mechanics with gravity? The journey is just beginning, and the answers may fundamentally alter our perception of reality itself. Quantum Internet and Gravity, a revolutionary breakthrough. The quantum internet, a revolutionary intersection with Einstein's gravity. Imagine a world where the principles of quantum mechanics and the fabric of spacetime intertwine in ways we have yet to fully understand. This is not just a theoretical dream, it is becoming a reality as scientists unveil groundbreaking research that explores the relationship between quantum networks and Einstein's theory of gravity. The rapid evolution of quantum networking. Quantum networking is experiencing swift advancements worldwide. As a cornerstone of the burgeoning quantum science field, it promises to create a global quantum internet. This innovative system would facilitate secure communication on an unprecedented scale and enable the connection of quantum computers across vast distances. Significant strides are already being made to bring this vision to life, both on Earth and in space. In a remarkable recent development, researchers have uncovered that quantum networks possess capabilities that extend beyond mere secure communication. A collaborative study spearheaded by Igor Pekovsky from Stevens Institute of Technology, alongside Jacob Covey from the University of Illinois at Urbana-Champaign and Johannes Borgard from Harvard University, has unveiled a new scientific avenue. Their research, published in PRX Quantum, indicates that quantum networks can be utilized to examine how the curvature of space-time affects quantum mechanics. This represents a pioneering experimental approach in this field. The uncertainty of quantum behavior in gravitational fields. While quantum theory has consistently withstood experimental scrutiny, its behavior in gravitational fields remains ambiguous. Einstein's general relativity redefined gravity, not as a force, but as a consequence of the warping of space and time, a concept referred to as curved spacetime. This curvature leads to extraordinary phenomena, such as the dilation of time near massive celestial bodies like planets. These effects have been validated with remarkable precision and have permeated popular culture, notably in science fiction narratives like the film Interstellar. But how does this alteration in the flow of time influence quantum mechanics? Is it possible that either quantum theory, general relativity, or perhaps both, need to be revised where they intersect? Although a comprehensive theory of quantum gravity is still elusive, there are indications that quantum principles may alter in the presence of curved space-time. However, exploring this frontier has previously been deemed impossible in experimental settings. Innovative methods with quantum networks. In a prior study published in Physical Review Research, Pekovsky and Borgard demonstrated that the time is ripe for experiments to delve into these inquiries using quantum networks. They illustrated how two distinct yet complementary aspects of quantum theory and gravity can simultaneously come into play. In quantum theory, superpositions exist. Matter can occupy not only specific, defined states but also mixtures of these states concurrently. Quantum computing leverages this principle to create qubits, superpositions of binary bits 0 and 1. Quantum networks can then transmit these qubits over extensive distances. However, in proximity to Earth, these qubits are also influenced by curved spacetime due to the changing flow of time. The researchers revealed that superpositions of atomic clocks within quantum networks would experience different time flows in superposition, thereby providing a pathway to investigate the relationship between quantum theory and curved spacetime. Igor Pekovsky, Jeffrey S. Inman Jr., professor at Stevens Institute of Technology, and one of the study's authors, remarked, "The interplay between quantum theory and gravity is one of the most challenging problems in physics today, but also fascinating. Quantum networks will help us test this interplay for the first time in actual experiments." Collaborating with Covey's lab, Pekovsky and Borgard developed a concrete experimental protocol. The team demonstrated how quantum effects can be disseminated across network nodes using entangled W states, and how the interference among these entangled systems can be recorded. By harnessing modern quantum capabilities, such as quantum teleportation, the transfer of a quantum state from one particle to another, and entangled bell pairs, maximally entangled states of 2 qubits, within atomic arrays, they can conduct tests of quantum theory in curved spacetime. Rethinking quantum networks' role in physics. We assume that quantum theory is universally applicable, but we really don't know if this is accurate, Pekovsky stated. It's possible that gravity alters the functioning of quantum mechanics. In fact, some theories propose such modifications, and quantum technology will enable us to test these ideas. The findings from Pekovsky, Covey, and Borgard illustrate that quantum networks are not merely practical tools for a future quantum internet. They also present unique opportunities for exploring fundamental physics that classical sensing cannot achieve. At the very least, we now have the capability to test how quantum mechanics operates within curved spacetime. References *. Probing Curved Spacetime with a Distributed Atomic Processor Clock. By Jacob P. Covey, Igor Pekovsky, and Johannes Borgard, 2025, PRX Quantum. DOI 10.48550/AR14.2502.12954. Testing Quantum Theory on Curved Spacetime with Quantum Networks. By Johannes Borgard and Igor Pekovsky, May 27, 2025, Physical Review Research. DOI 10.1103/PhysRev Research.7.023192. Stay updated on scientific breakthroughs. Never miss a breakthrough. Join the SciTech Daily newsletter.